Hey, Wheaton North, Mr. Yergler here. Let's get some more practice with dimensional analysis. Now we're on to multi-step problems, so we'll have to kind of plan our steps as we go. You should be comfortable with small single-step problems. You should be getting the hang of dimensional analysis. This is kind of review for a lot of you, so if you need help with more simple dimensional analysis or understanding it, make sure you go back to those other videos, ask questions in class, and make sure you get that straightened up, because dimensional analysis is just a skill that we're going to use to solve lots of chemistry problems. So just like how you have to know how to solve an equation in algebra or in math, you use that skill throughout all of math. We're going to use dimensional analysis the same way. All right, we're just going to go through two examples, and I'm going to do them on paper. So calculate the volume of 13.80 grams of argon gas at STP. Remember from the previous video that STP is kind of an indicator that we have a specific relationship, a conversion factor that we can use. At STP only, that's standard temperature and pressure, it's 0 degrees Celsius, 273 Kelvin, and 1 atmosphere. At STP, a mole of gas is 22.4 liters, so we can use that as a conversion factor, and we're going to need it. Let's start with what we're given. 13.80 grams. I'm writing the 0 here, even though it doesn't really affect the calculation, because when I look back over my problem, I'm going to want to see that I have 4 significant figures there. If you drop that 0, you'll think that it's 3 sig figs. Even you'll forget to go back to the original given up here. Now I can't go from grams directly to volume. There is no grams to volume conversion, and so I kind of need to stop at moles, just like that molar map showed on the previous video. So we're going to go from grams to moles, and from moles we can get to anything. We can get to volume at STP. Okay, so that's kind of our flow chart. So let's go to moles. Argon gas's molar mass is 39.95 grams per mole. I'm writing it upside down so my grams will cancel. And then let's just keep going. No reason to stop and calculate because we can go right into volume. We've canceled grams. Now we need to cancel moles. So I'm going to put 1 mole, and that's going to cancel, under 22.4 liters. Now we're left with liters, volume, which is the unit that we're looking for. And you get 7.738 liters. Okay, the next example, water decomposes into its elements when electrified at high voltages. So that's going to be hydrogen and oxygen. If 24 grams of water is completely decomposed, how many grams of oxygen will be produced? We need to have a chemical equation, a chemical reaction to go off of with this, because the mole ratio is going to be important. Hydrogen and oxygen are both diatomic, so it has to be H2 and O2. To balance it, we need a 2 here and a 4 there. Whoops, I'm sorry, we need a 2 there. 4 hydrogens total. Okay, so let's start with what we're given. We're given with 24.0 grams, and I'm going to write out that it's water, and that's important in this case because we're going to switch from one substance to another. We're going to go from water to oxygen. Now, let's kind of write out a flow chart to kind of help us. We can't go from grams of water directly to grams of oxygen. We can't even go to moles of oxygen yet. We first have to go to moles of water. From moles of water, we can go to moles of oxygen with our mole ratio. It's going to be 2 to 1 because our equation is balanced. And then we can go to grams of oxygen. So let's get started. We need the molar mass of water, which is 18 grams per mole. And this is moles of water, right? I'm going to keep that in there because right here it's easy to kind of get them switched around and forget what is it that we're talking about. 2 moles of water creates 1 mole of oxygen. From moles of oxygen, we can cancel moles of oxygen and get grams of oxygen. The molar mass is not 16, it's diatomic, so it's 32 grams of O2. So moles cancels, grams cancels. Everything's gone except grams of oxygen, which is exactly what we want. It ends up being 21.38 grams of oxygen. So there's a couple more examples of dimensional analysis, now with several steps and even throwing in an equation, which is something you'll start to see a lot, where you're asked to just, the question kind of assumes that you're able to just go from these words into a balanced equation. And then from there, you can go into the dimensional analysis. All right, this is Mr. Yergler signing out.